Hey everybody! Today we will try to implement a fun paper called Learning Mathematical Properties of Integers. You can see the paper on the screen. Unfortunately, the source code was not published, and therefore all the code in this video is going to be my best guess on what the actual implementation could look like. As always, I'm in no way associated with the authors, and all credit goes to them, and I would definitely encourage you to read the paper. By the way, this video has multiple sections, so feel free to jump to whatever section you like. And if you don't care about the coding part, feel free to skip all the way to the end where I show the results and nice visualizations. Anyway, the idea of the paper is really simple. We want to take integers and embed them. Embedding is nothing else than assigning a vector of numbers to each of the integers. So let's say we fix the dimensionality to 5, and this is how the final embeddings could look like. Ideally, we would want these vectors to encode all relevant properties of integers. For example, their actual value, whether they are divisible by 2, whether they are prime numbers, the number of digits, and so on and so on. Okay, so now that we understand the goal, how do we actually create or learn these embeddings? There are two ways. First of all, we can just take a pre-trained language model that already computed these embeddings for us. Language models embed tokens rather than integers. However, an integer is a special case of a token if we see it as a string. In this video, we are going to look at the BERT embeddings and the GloVe embeddings. Anyway, the second approach is to pick an embedding technique yourself and apply it on a custom dataset. We are going to download a bunch of sequences of integers that have patterns in them. What do I mean by this? Let's take the Fibonacci sequence, for example. As you probably know, the pattern here is that we can simply obtain the next integer by summing up the previous two integers. So in order to be able to understand and to predict what the sequence is going to look like, you need to understand the concept of addition. Okay, so what technique are we going to use to get embeddings from our data? There are multiple options. In the paper, the authors benchmark the LSTM network, latent semantic analysis embeddings, and fast text. In this video, we are going to focus purely on the LSTM approach. The idea is to process one integer at a time, always trying to predict the next one while using the knowledge of what the previous integers were. And we're hoping that a network that is trying to solve this task will be implicitly forced to learn meaningful integer embeddings. When it comes to downloading the sequences, we are going to be using this website called the Online Encyclopedia of Integer Sequences. It is pretty impressive because it stores more than 300,000 sequences. You can use the search functionality to match your sequence to existing sequences in the database. And as you can see, each sequence has a unique identifier. Anyway, our goal is to actually download every sequence there is and create a training set out of it. To do this download, I actually had to look around quite a bit for different solutions. And luckily, I discovered that there is an API that, given a sequence identifier, returns a JSON file with all the necessary information, including the actual sequence of numbers. I wrote a Python script that does this download. Just note that it might take a bit of patience since they have limits on the API usage. All right, so let me show you how the raw dataset looks like after the download. So I have it lying locally in this pickle file. And as you can see, there are 340,000 sequences. Let's check out some of them. So yeah, as you can see, it's just a list of integers. Another one. However, one important thing that we will need to deal with is the fact that these sequences have different lengths in general. Let us quickly investigate what is the length distribution. So the mean length seems to be around 43 integers. However, the standard deviation is quite high, 28, so it can really vary. And the second thing we would like to look into are the actual integers inside of these sequences. So here we just concatenate all the sequences into a single huge sequence. And as you can see, there are more than 14 million integers. Here we counted up the number of occurrences. And here we can see the 20 most frequent integers, and the result is actually not that surprising. However, we can also inspect the least frequent integers. There are these huge integers that only showed up once in the dataset. There's around 1.7 million different integers. All right, let us now write a couple of utility functions. First of all, we want to write a utility dataset class that is going to take our raw dataset and adjust it so that we can directly use it in training. Right, so the first parameter is nothing else than the raw sequences that we just looked through. The second parameter is something we choose, and it is going to be the sequence length. So there are two possibilities. If the original sequence is longer than this, then we will simply cut it off after this specified length. And on the other hand, if the original sequence is shorter than this, we will just pad it so that it has this sequence length. Finally, there is an argument max value, which is the maximum integer that we allow in the sequence, and it is non-inclusive. For example, if we set it to 3, then we only allow sequences that are composed of the numbers 0, 1, and 2. And when it comes to the internal attributes, we will actually create a NumPy array that is going to have a fixed shape. It is going to be 2-dimensional, and the number of rows is going to be equal to the number of sequences, and the number of columns is going to be equal to the sequence length. And the reason why we want to actually have this constant size array is to be able to just stream its rows as samples for our deep learning training. And the fact that all of them will have the same length will allow us to do batching. The goal here is to kick out those sentences that had some elements that were below 0 or above our max value that we specified in the constructor. And here we just initialize our normalized sequences, which is a NumPy array, and we make sure that the D type is just int 64. And the reason why we populate all the elements with max value at first is because it will serve as a unique identifier, saying that a given element of a given sequence is out of range. Later, we will just make sure that all elements that are equal to max value are not going to be taken into account for the loss function, and also we're not going to compute any embedding for them. And here, sequence by sequence, we populate the normalized sequences array. Here we just define the length of the data set. And finally, we define what it means to get a sample, and it is nothing else than querying our normalized sequences array at a selected row. Let us now just play around with this custom dataset that we've just implemented. So first of all, let us again load the raw data, which is just a list of lists of integers. And now let us just investigate how big our custom dataset is going to be depending on the two parameters, max value and sequence length. So here we set the max value equal to 100, which means that all elements of the sequence need to be in the range 0 and 100, and we only actually extract the first 20 elements of the sequence. And as it turns out, there are around 97,000 sequences that satisfy this condition. However, now we are actually going to increase the maximum value, which means that there should be more sequences that actually satisfy this requirement. And it is indeed the case. Now we are requiring the first 100 elements to be in the range 0 and 2000. And actually it is lower than the previous dataset, which makes sense because it is more restrictive. And here we actually assign the dataset to a variable, and let us see how the samples look like. So as you can see, this sequence has 100 elements, and the last 6 elements were padded with the max value, which was 2000. The second sequence has again 100 elements, and it is going to be the case for all of them because that's how we designed it. And here no padding took place. The original sequence had more than 100 elements and we just cut it off. All the sequences have elements that are larger or equal to 0, and at the same time they are smaller or equal to 2000. To summarize, we used padding and truncation to make sure that all sequences are of the same length, and we made sure that all the elements are in a fixed range, where the maximum value, in this case 2000, will basically tell us that we should not count this element towards the loss function, or that we shouldn't create an embedding for it. Alright, so we're back in the util script and we would like to implement our neural network. So the first parameter here is the max value, and we've already seen this parameter with the custom dataset. And it basically dictates how many embeddings we are going to create. Embedding dimensionality just determines the dimensionality of the embeddings, not surprisingly. Then we will have a LSTM recurrent neural network, and it has 2 parameters, so which is the number of layers and the hidden dimensionality. And we will take the hidden states of the LSTM network and we will actually run them through a linear layer, and this parameter determines its dimensionality. And internally we will have a couple of modules. First of all, we will have the embedding module that will actually store per integer embeddings. Then we will have an LSTM network that is going to take these integer embeddings and spit out hidden states. And then we will have a linear layer that is going to take a hidden state and transform it. And this transformed hidden state then goes to the classifier, and the output of this is the logits over all possible integers. So first of all, we instantiate the embedding module and we provide the corresponding parameters. What's interesting here is that the number of embeddings is going to be max value plus 1. However, as you can see, we set the max value to be the padding index, which means that we are not going to learn this embedding and it is going to stay constant zeros throughout the entire training. Here we instantiate the LSTM network. Size of the input is nothing else than the embedding dimensionality. Finally, we instantiate 2 linear layers. The first one is just going to transform the hidden states, and the second one is going to take these transform hidden states and then output the logits across all the possible integers. Right, the forward method is going to take a batch of sequences, and what we returned is a tensor of logits. It holds the probability distribution over all different possible integers of what the next element is going to be. and we would actually need to normalize it to get a probability distribution, and this is done with softmax. However, this is going to be done inside of the loss function. Alright, so we run the input tensor through the embedding module, and what we get is for each element in our sequence, its corresponding embedding. And then we take this embedding and run it through the LSTM network. One way to interpret this is that for each element in the sequence, we have a hidden state, and this hidden state should encode all the integers that we have come across up until now, and it should help us to predict what the next integer is going to be. And we take these hidden inputs and we actually apply the same linear mapping to each and every one of them. And finally, we take the dense tensor and we run it through another linear layer, but this time the output features is equal to all the integers that we are considering, and it is going to be the logits. All right, and let's try it out. So I define the batch size to be 1, the sequence length 10, and the max value 20. Instantiate the network, and now we want to create some random input. And let's run the forward pass. So first of all, we see that it has the shape of batch size, sequence length, and maximum value. And what you can see here is the network's prediction of what the first integer could be. This is the prediction on the second integer, third one, and so on and so on. Of course, the network is not trained. Everything was just randomly initialized, so we're getting more or less like uniform distributions, but we're hoping that after training, this will actually be meaningful. Now we just need to write a couple of evaluation utilities. All right, so the goal of this function is to take integer embeddings that would be encoded in this X feature array, and given a target array, let's say representing divisibility by 2 or primality, we want to evaluate how good a simple logistic regression classifier is at predicting the target label. We create a stratified k-fold. The reason why we want to stratify is because some of the labels will be very imbalanced. For example, if we inspect divisibility by 10, then it's only like 10% of the data set that has this label. Here we create a scikit-learn classifier that is nothing else than a pipeline where we first scale the features and then we run the logistic regression. Here we use the cross-validate function from scikit-learn that is going to run cross-validation, and it is going to return the accuracy over all faults, both training and validation. And finally, we compute the average accuracies just by computing the mean over all faults. And the last function we want to write is a function that will just create the target for us. We just take the numbers that the user provided as input and we create a bunch of binary classification targets. So before we start training the LSTM network, let us first try to download some existing embeddings that are out there for free. First ones are the GloVe embeddings. I'll give you a link in the description where you can find the embeddings. I already downloaded them, and let me just show you the first line of this file. These embeddings have the dimensionality of 300, and the way this file is structured is that all the values are space separated, and the first entry is always the actual token, and the remaining entries are just the floats. For example, here it's the token the, and all the numbers after it represent the 300 dimensional embedding. So let us just quickly write a script that parses this data set, and also we want to visualize it with TensorBoard. So we define a command line interface and we parse all the arguments. We create a TensorBoard writer. And now the goal is to parse the text file. First of all, we will create this toFind set that is going to consist of all integers 0, 1, 2, all the way up to the maximum value evaluation. And we actually need to cast it to string because when we read the text file, everything will be seen as a string. And here we just pre-populate an empty array, NumPy array, that is going to store the final embeddings. So we open our text file and we go through it line by line. And as shown before, the first element on the line is going to be the token itself, and the rest is going to be a vector of floats. Just cast it to integer, and then we populate the corresponding row of the embeddings array. And once we iterate through all the rows of our text file, we just want to make sure that we found all the integers that we were looking for. We just create all the consecutive integers from 0 all the way up to maximum value eval, and then we use our helper function to create classification targets. We just prepared metadata for TensorBoard. For each target, we train a classifier and compute the train and test or validation metrics. And we track all these metrics with TensorBoard. And finally, we also add our embeddings plus all the metadata. And that's it. All right, let us now write a script that is going to get the BERT embeddings and track it with TensorBoard. All right, so the idea here is that we are going to fix a specific model. In our case, it is the BERT based uncased. We instantiate a summary writer for TensorBoard tracking, and then we also load a tokenizer and a model from a pre-trained checkpoint. Similarly to what we did with GloVe, we take the integers of interest and we cast them to strings because the vocabulary of the language model consists of strings. And we take each of our integers and we try to understand what position in the vocabulary it has. Unfortunately, it can totally happen that some of the integers are not in the original vocabulary and they are implicitly mapped to the unknown token. And we're only going to run the evaluation on those integers that are in the vocabulary. And this numbers array is only going to store the integers that are in the vocabulary. So this is basically how we access the embeddings module, and then you can just call it to actually get the embeddings. We create a couple of different binary classification tasks, and then we use logistic regression to solve all of them. And then we track the accuracies with TensorBoard. And also we visualize the embeddings. Yeah, that's it. All right, and finally, we would like to implement a training loop for our custom LSTM embeddings. All right, so we defined the CLI, and I guess we've seen all of the parameters before. Here we instantiate the device, and we also hardcode how often we're going to evaluate. We instantiate the TensorBoard writer, and we dump all the CLI parameters as text. Here we load the raw sequences, and as you saw before, they are just a raw download of the Encyclopedia. Here we instantiate our custom dataset, providing both the maximum value and the sequence length. Here we create the histogram of the integers in our dataset to be able to better understand what the distribution is. And here we create a data loader. We instantiate our network. We make sure all its parameters are on the right device. Here we instantiate the cross entropy loss, and an important point here is that we set ignore index equal to the maximum value. Here we instantiate an optimizer. The previous lines are exactly the same thing we did for the BERT and GloVe embeddings. We're just preparing the binary classification problems and embedding metadata for TensorBoard. What's going to be different is that we are actually going to run the classification multiple times during training whenever we evaluate, whereas for the GloVe and BERT embeddings, we just ran it once because we already took pre-trained models. We make sure that the batch of integer sequences is on the right device. And we run the forward pass, and as output we get the logits. And then we just permute them in a way that we can use them directly in the cross entropy loss function. And also note that we are discarding the last element of the sequence because we don't necessarily have the ground truth for them, because we don't know what is going to happen in the sequence length plus one step, because the sequence stops there. And when it comes to the targets for the loss, we always cut off the first element of the sequence because we don't have any predictions for it. Finally, we actually compute the cross entropy loss. And if I'm not mistaken, it should be computed for each element in the sequence separately and then averaged. And that's why we just end up with a scalar. This is Torch boilerplate. And here we track the loss after each step with TensorBoard. And the only thing left to do now is to write evaluation logic that is going to be run every couple of steps. So here we extract our embeddings. However, we only take the first max value of val integers because we don't want to evaluate on everything. So the reason why we want to evaluate only on, let's say, the first 500 integers is because, as you saw, the dataset has a huge sparsity when it comes to higher integers. And we just want to make sure that we run the binary classifications on the subset of the embeddings that are probably pretty good, because the numbers from 1 all the way to, let's say, 500 are integers that showed up in the vast majority of sequences. And here we track the embeddings with TensorBoard. Again, we iterate through all the different binary classification targets like divisibility by 2, and then we fit a logistic regression model. Finally, we track the accuracy with TensorBoard. And also we save the current model each time, overriding any previous checkpoints. And that is it. That's our training script. Now let me show you the script that we're going to run. First of all, we're going to parse and track the GloVe embeddings. Then we're going to parse and track the BERT embeddings. And finally, we are going to launch the training script for our LSTM network. Here you can see all the important hyperparameters. Note that the maximum value of val is always 500, which means we will be evaluating and embedding the first 500 elements, which means that we will be evaluating on the first 500 numbers. Unfortunately, BERT actually does not have some of these integers in the vocabulary, but whatever. All right, so I'm just going to launch the training now, and hopefully I'll have a result in a couple of hours. All right, first of all, let us take the model checkpoint and try to see how good it is at predicting the next integer in a sequence. So this is our model. I'm sure you recognize it. And let us now write a helper function that is going to take in an input sequence, and it is going to output the prediction of what the next integer could be. K will determine the top K results that we're going to display. We create a torch tensor, and we also add the batch dimension. We run the forward pass, however, then we just take the first sample, because that was just a single sample in the batch, and then we just take the very last prediction in the sequence because we want to predict the next element. We take the logits and turn them into a probability distribution by using softmax. And we simply extract the top most probable values together with their indices. So we start with a very simple sequence, and as you can see, the model got it right. It is 80% certain that the next element is 7. Again, it got it right. When it comes to the powers of 2, it seems to understand what's going on. This is just a sequence of primes, and again, it got it right. Let's try to extend it. 19, which is correct. 23, which should be correct. So as you would probably agree, it learned something about the integers, and maybe this is just a result of overfitting the training set. However, the training set is huge, and our primary goal was to inspect the resulting embedding, which we're going to do now. All right, let's go through the TensorBoard results. First of all, you can see that there are multiple scalars. Most notably, there are accuracies of the logistic regression model when we use the integer embeddings as features. and the targets represent whether a given integer is divisible by a certain number or whether it is a prime. We only run this classifier on the first 500 integers. On the left, you can see that we have three different models: GloVe, BERT, and LSTM. And LSTM is the only one that we had to train from scratch, and that is why its performance will change over different steps. If you look at the divisibility by 2, we see there are two plots. The one on the left represents the mean test accuracy, and the one on the right represents the mean train accuracy. I guess all these results should be taken with a grain of salt, since we used a very basic classifier, the logistic regression, and the number of samples is actually not that far away from the number of features. Anyway, it seems like the LSTM embeddings carry all the necessary information to determine whether an integer is even. The BERT embeddings come second. Moving to the divisibility by 3, it seems like the LSTM embeddings are again the best. Just for the context, if we always predicted that a number is not divisible by 3, then we would have an accuracy of around 66%. So that is definitely a benchmark we are able to beat with the LSTM embeddings. Same story here, the dummy benchmark would be 75%. However, when it comes to divisibility by 5 and 10, it is a different story. Clearly, the embeddings that were trained on a big text corpus are better than our custom-made LSTM embeddings that were trained on integer sequences. I'm not really sure why that is. However, yeah, if you have any ideas, feel free to share them. Anyway, if you look at the prime classification, again, our LSTM model is by far the best one. And finally, here you can see the training loss, and maybe I could have continued the training. However, I just stopped it after approximately 16 hours of training on a single GPU. Here you can see the distribution of integers in the sequences that we use for training. First of all, after filtering, we were left with approximately 140,000 sequences. Again, the reason why there are so many integers equal to 20,000 is because we use this value for padding purposes. Here we have the GloVe embeddings, and they all have the dimensionality of 300. We apply the principal component analysis to extract the three most important directions. And as you can see, these directions explain 37% of the total variance, which is a very high number. And in a way, it is telling us that the GloVe embeddings actually don't really pay that much attention to integers, and instead they focus on semantics of a language. It is obvious that these embeddings clearly understand the order of integers, since all the points are clustered by the value. So here we have all the small integers, and as we move on to the left, or whatever it is, we get the big integers. What is interesting is that if we look at the integers divisible by 5, we can see that they are quite clearly clustered together. And this is why it was so easy for the logistic regression to solve the classification problem. Moving on to BERT embeddings, the first thing to note here is that we only have 390 points, and that is because there were 110 integers that were not present in the BERT vocabulary. And also the dimensionality is 768, which is way bigger than the GloVe embeddings. The total variance explained by the three principal components is 28, which is way less than the one for GloVe. And let me also show you the UMAP dimensionality reduction. There are multiple clusters here, it seems like. And again, if we highlight the numbers divisible by 5, we see that they are definitely grouped together. And finally, let us look at our custom LSTM embeddings. We were able to embed all 500 integers, and the dimensionality is 128, which is the smallest out of the three models. This checkpoint corresponds to the randomly initialized embeddings at the beginning of the training. And as you can see, there is no pattern here. However, if we look at the last checkpoint, we clearly see that, again, the embeddings do encode the actual value of the integer. The explained variance is 7%, which would suggest that our embeddings contain a lot of information, and by performing a dimensionality reduction, we actually lose a lot of it. If you look at the UMAP dimensionality reduction, it seems like there is a bigger continuity between the embeddings, which I would probably attribute to the dataset we trained the model on. Anyway, if we annotate our points based on the classification targets, let's say divisibility by 5, or whether a given number is prime, or divisibility by 2, there does not seem to be any clear patterns, and again, that is probably because the dimensionality reduction threw away a lot of useful information and only focused on the directions that encode the actual value of the integers. Anyway, that's it for today. As always, I will put the code on GitHub, and if you have any feedback, especially ideas how to make these videos better, then I would be more than happy to hear from you in the comments here or on other platforms like Discord. Don't hesitate to subscribe and like the video, because that's definitely one of the things that motivate me. Anyway, have a great rest of the day, and I will see you next time.